our speaker now is Professor Jozef from George Washington University, and he will be talking to us about homology of Yang-Baxter operators from Lou Kauffman, Braids paper to HOMFLYPT Yang-Baxter homology. So, Professor, whenever you're ready.
Thank you. Thank you. So I am sharing. And here is okay. This is not the beginning. I will see whether I understand how it works. No? I don't know how it works. Oh, now I know. Very good. So it is great pleasure to give a talk and celebrate 80th birthday of Lou Kauffman. And in my talk, of course, title is saying everything, but in my talk, I will try to see from time to time how important was influence of Lou Kauffman for my endeavors. So let's start. So first, I will read and comment my abstract, which is overbearing. Okay, so, but I start with visit to Saragossa to visit Jose Montesinos. So in the spring of 84, I traveled to Saragossa to visit Jose Montesinos. I was then working on incompressible surfaces with Maite Lozano, so co-author of Jose as well, and just discovered the conjectural smallest volume hyperbolic trimanifolds. So I talk about this in Saragossa. However, Jose told me that just Lou Kauffman, I didn't know much about Lou Kauffman then because I was not working on Knot Theory. However, I knew his paper about Alexander Conway polynomial. So anyway, Jose showed me notes by Lou Kauffman, who visited Zaragoza just before me. Maybe still it was May or maybe April. And he showed me notes from his talks. Later, I learned that these were notes for a future book on knots. So we know this book very well. So what caught my attention was reference to work by two physicists, Boll and Mehta, on the inductive proof of the existence of Alexander polynomial. So Lou incorporated in these notes outline of the proof. So it was nice inductive proof, unlike other proof using Seifert matrices or Alexander matrices. So a few months later, we were able with Paweł Traczyk to show. So I knew already, no, then I didn't know, but I learned later about John's polynomial. So with Paweł Traczyk, when we generalize John's polynomial to, I call this HOMFLYPT polynomial, I'll call it usually generalized John's or HOMFLYPT polynomial, kind of we were ready to prove this. And proof was much more complicated, but we use just rather involved induction. What is interesting was this observation by Paweł that if you relax condition and we don't have polynomial relation, I mean linear dependence, but just abstract magma relation, then still we can produce some invariants. And we formulate some relation, which we called Conway relation. I didn't know that it's well known in non-associative algebra relation with many names, but some people call this entropic relation, and I am calling this entropic relation. So then, as in this abstract, after this few months of intensive work, I should say that we were working in Joanna's small apartment. We didn't have other place to work with Joanna Kania-Bartoszyńska baby under the table, but still it was very fruitful work. So then many 30 years, almost 30 years later, I realized how to, first of all, Jones gave description of Yang-Baxter operator, which is giving HOMFLYPT polynomial, substitution in HOMFLYPT polynomial. So finally, in 2012, I realized how we can define homology of these Yang-Baxter operators, in particular with small modification, this one which is giving HOMFLYPT polynomial. And this was my work in the last several months. And I will say a few words about this. It was work with my students and former students, rather nice, unexpected generalization, I mean work, because we did more than we planned, but it will be later about this. So here I still write that we are compute. Yes?
I'm sorry to interrupt you. We have a comment Would you please make bigger the screen because
Okay, I can make bigger screen, of course.
perhaps 150 would be.
Yeah, then I have to go differently by page. Do you see now?
Uh,
It is still the
yes,
same
that's okay.
title page. So when I really would like to show something, I will make very big. Otherwise, probably I will move sometimes page by page because there's too many pages. As you can see, there's 40 something, I don't know, 51. Anyway, but some paper. Okay, so this was this history which I was saying. Let me see whether I know how to move along this. Yes, so you see, I would like to talk about too much, about history, about technical things in history, and then technical things which lead to me to homology of Yang-Baxter operators. I will mostly concentrate, you see, plenty of chapters, but of course I will skip over them mostly, but I will concentrate on things related to Lou Kauffman 80th birthday. So anyway, so as it's written here, maybe I will read this. My talk is composed of two parts. In the first part, I give a historical introduction to not Torre, starting from Leibniz Geometria Situs and mentioning the mathematicians, philosophers who influenced Leibniz greatly. I mention this because it's not that well known. It is Ramon Llull or Ramon Llull, but probably Ramon Llull, or it should be double L, not one L, and Anastasius Kirchel. So here I learned much more about Llull when I was visiting Maritania Silvero, with whom I work a lot. In Barcelona she was, so yes, in Barcelona there's even University of Ramon Llull, and there is monument of him. So anyway, he's well remembered, but not that well known, but Leibniz was mentioning him many times. The same with Anastasius Kirchel, even more. I will go to this footnote about Kirchel. This is Polonika, that in Poland there is now Olga Tokarczuk, who got Nobel Prize in Literature, and in one of her books, he's mentioning first Polish encyclopedist, Benedykt Chmielowski, and when I was in school, teachers usually were laughing from this encyclopedia, but in fact it's a pretty nice, serious encyclopedia, and for Chmielowski, the main source was this Kirchel, there are Kirchel books, very nicely illustrated Kirchel books. And Leibniz as well, for the same reason that his father was keeping Kirchel books in his library. Leibniz was very much motivated by Kirchel. Some people even say that most of the ideas are taken from Kirchel. This overstatement. Anyway, at the beginning of the second part, I described attraction of non-associative structures and how my work with Paweł Traczyk on generalized of the Jones polynomial led us to entropic structure. This I mentioned that not only linear relation giving HOMFLYPT polynomial, but entropic equation. I will mention later, but of course I will skip over this. So finally, the work on HOMFLYPT polynomial led me to the scale modules, which was one of the main topics I was working in the last 40 years. So, and then I said I will be about N moves, about some interesting formulas, but really mostly I'm interested in last months in the Yang-Baxter homology. I will mention this shortly, but mostly I will talk about history of not-Tori. So as I said, the path, many digression, etc. But as it is written on the bottom, in practice, most of the talk will be history of not-Tori and history of my interactions with Lou, two stories that have been intertwined over the last 50, 60 years. Probably Lou will protest that 60 years, but probably closer to 50. 50 years. Okay. So now interaction with Lou. So of course, first is this short title that Lou think about himself, I believe, as successor of John Conway. I think Lou wrote very nice essay. I think it was about Conway, when he said that Conway visited Princeton, was showing his standard very nice tricks, not Tory tricks, and gave beautiful talk, and Lou became kind of his discipline. Lou already was then postdoc, so he had PhD, but he thinks about himself as Conway disciple. Okay, so now this is my interaction with Lou. So this is already, I said that my first real interaction was when I did see this Lou Kauffman notes, future book on knots with Bolland meta-inductive proof of the existence of Alexander polynomial. So this is repeating, so maybe other story. So our paper with Paweł, we couldn't really send to the West because of censorship. So formally we should give our paper to censor and he could keep it for maybe only 1 week, but he could keep 2 years as well. So somehow we smuggled this with help of Jose, and he was showing this paper in US. I think there was some low dimensional conference in spring of 84. And Lou Kauffman did see the paper, probably we asked to give him, and he answered us by mail that this beautiful paper. This was very nice of Lou because we were very isolated with Paweł in Poland. So after this, we can kind of became in much better spirit. And as I wrote here, Paweł, I think it was in January, was drafted to army, so he couldn't make final touches of the paper. Then it delayed our paper a little, but it was essentially written. I think even with Joanna in December, we submitted very short version to Delta, to journal for high schoolers. Anyway, but this note by Lou, beautiful paper, really was maybe crucial that with Paweł we decided to work on knot theory. As I wrote here on the bottom, Paweł was working then on compact transformation groups, and I was working on incompressible surfaces and smallest volume hyperbolic manifold. Doesn't like to go further. Yes. So now, as in the title of my talk, I said that with respect to Yang-Baxter operator or general statistical physics, big influence was Lou Kauffman paper in the proceedings of Braids conference. Conference was in 86, in summer of 86, kind of satellite conference to Berkeley Congress of Mathematicians. So Lou wrote the paper Statistical Mechanics and the Jones Polynomial. So as I wrote here, this was very new to me and really eye-opening. But I am not absolutely sure whether I was at Lou talk, whether really Lou gave this talk in the conference, because I only remember reading this paper in proceedings called as Conference Braids. I think it was organized by John Bierman and Von Jones, and there was some biological part, Cosarelli. Anyway, so again, as I wrote, possibly Jones was talking on Yang-Baxter operator. However, this I don't remember, but we know that that summer he gave talks in Sussex, and it was important because Vladimir Turayev was in audience, and both of them independently wrote paper about this. Turayev paper is kind of important because he's using braids, and maybe they are equivalent, but somehow his paper was easier to generalize and understand. And in fact, a few years later, I was giving even talks about, in Michigan State, I think, about this paper. So here I copied from Mathematical Review for Maths.net now, review of this Lou Kauffman paper, and maybe as tribute to Lou, I will read this again, written by Temperley. This is the Temperley of fame of Temperley Lib. So Temperley writes, this paper studies various relations between the recently introduced Jones polynomial for braids, links, and knots, and Collering's problem for graphs. In particular, the calculation of the dichromatic polynomial and the Potts model partition function for a graph. The deletion contraction algorithm for solving such graphical problems turns out to be equivalent to taking the medial of the graph studied and progressively removing crossing from it by the use of surgery triple. with suitable changes of variable, this calculation also derives the Jones polynomial for a link related to the medial graph. Relation with vertex arrow covering problem in statistical mechanics are also pointed out. So this is the first time I heard about connection with statistical mechanics. And as I said, a few years later, I was invited by Selman Akbulut and I gave series of talks on Turayev paper. And we use this paper till now. Okay. Okay, so now I was trying to test my memory and sometimes not that good exercise. So I copied here a few times. I met Lou Kauffman for sure, especially if it left on me some big impression. So first I already mentioned Saragossa 84, notes for the on notes paper. Then this art in bread group. So here I wrote precisely Santa Cruz, July 86. Then was this curious conference in Chicago. So when I went as postdoc to Dale Rolfsen, very early, I think October or 86, he took me to the conference in Chicago, which Lou Kauffman was organizing. And of course, the most memorable thing was negative that with Dale we were robbed in the hotel where we were staying. So I don't remember much about conference, but probably it was the first time I really met Lou Kauffman. So this conference of Braids is not sure whether I really talked to Lou, or maybe he was not there on the road paper. Okay, now outcome of HOMFLYPT polynomial was this construction or maybe discovery of the Kauffman bracket scale model and other scale models. So I wrote it April 1187. So then Lou made me associate editor of Journal of Not Theory. So this was important thing from November of 95. Also not 96, but November 95. Then very important thing was not in Hellas, but I think Sofia was talking at this a lot and showing very nice pictures from Not in Hellas. So I will skip this, but it was very important. Then there was conference not in Vancouver. And I wrote here the title of my talk. It was about Chowanov homology. So maybe I should stop for a moment about this, about go to mathematics, or rather my dream for a moment. So Chowanov homology is categorification of Jones polynomial or Kauffman bracket model. We are computing homology of Yang-Baxter operator giving Jones or HOMFLYPT polynomial. So must be some relation. So my dream is, this may be realistic and maybe some other people do soon, find relation between Chowanov homology and Yang-Baxter homology. It's not clear on which level it will be, but for sure both of them are generalization of Jones and HOMFLYPT polynomial. Big dream is to see Chowanov homology as kind of responsible for phase transition in some statistical mechanics models. And here, this first paper of Lou Kauffman was showing that already Kauffman bracket is related to Potts model or maybe Ising model or something in between. Okay. Then there was this Vancouver conference. I think I already mentioned this. I mentioned this twice, I see here. Then there was big conference in Trieste, which we organized with Lou, with Sofia, and with Slavik Jablon. Then many not theoretics, especially from outside of Europe and US, were there. And maybe finally, 10, not finally, but 10, you see speculative distinguished 1st of April talk, and Lou was talking about four-color theorem. It was very fascinating, and it was very much related to Lou talk, which he gave 2 days ago, yeah, four-color theorem. So in this talk, he gave 4 proofs of four-color theorem. And of course, each of them has some defects, as we can expect. But it was kind of almost funny, because when he was finishing his last proof, came some person and told us that we have to leave immediately the room because the next class or next whatever is there.
So I
So
didn't
then
get to
always said-
finish my proof.
Yeah, exactly. Yes, Lou. Then he didn't let you to finish the proof, and maybe it is lost now. So, so this was 2012. So we have still till now the speculative distinguished 1st of April talk. We have sometimes very interesting speculation, Lu, etc. Then somehow my memory came to Aspen. I wanted to say that, but it's not totally true, that we went skiing with Lu, but we just took ski lift and go up the mountain and then just walking there. So this was 2018. Then came COVID. And you see this last thing which I choose is conference and workshop in Australia. And this is kind of little sad. So later I will be more positive. But here Lou couldn't come, but at least he was participating by Zoom. But I came, but I will show this picture. This is next slide. You see, now I can make even bigger. So you see, Lou was giving before talk by Zoom. But you see, I'm in rather bad shape. So I fall there and hit my head, and probably it was the only time I came to classroom for the picture. Still, we're working with students. But anyway, this is probably the last conference we're kind of together. This is this summer, June of 2024. I can make this picture even bigger. You can see now. Okay, so this is this chaotic memory of meeting Lou. Of course, there was much more. So let's go make it smaller now and go further. So as now it is obvious already, I spent half of my talk almost. So I will talk very little about Yang-Baxter operators. Mostly I will talk about history of knot theory, and Yang-Baxter will be only maybe there. So I will mention the theorem we're working already for some times with Xiao Wang, my former student, and still when he was student. So for example, this conjecture, which you will see in a moment. Let's go up. This conjecture was, I think, is 9 years old when he was student, but eventually we solved this, as you see here, now proven January 2025. So I should praise my students and former students. We computed third homology, whatever it is defined, Yang-Baxter operator giving HOMFLYPT polynomial on level M. So people who care about this know that it's on kind of SLM version of HOMFLYPT polynomial for every ML substitution, but we have one formula. So this is very nice. What is curious here is that it has two types of torsion, only two. And whatever we computed, because computed more, we computed fourth homology recently, always there's only torsion 1 minus y squared and 1 minus y to the fourth power. I would say I would expect 1 minus y to any even power, but no. So this we prove. So I will not talk about proof, but this is first step of understanding Yang-Baxter homology. I will show one picture of definition. In fact, you can define Yang-Baxter homology of Yang-Baxter operator, just definition without words. Graphical definition, again in tradition of Lou Kauffman, is almost sufficient and very good for some calculations. Okay, let's make it smaller. Then we can move page by page, because now I will move with history, so only with some pictures I will show it bigger. Okay, that's all. Then we prove the conjecture, and here we work on the conjecture. So maybe still bigger. You can see my students working on homology of Yang-Baxter operator. I hope you can see now. So let's look at us for a moment. So this was when we were still struggling with conjecture. Now it is proven. Okay. So now history. Let's make this smaller. However, I like very much this picture. So this is almost 4,000 years old from Sumeria, and this merchant chose as his stamp very nice fall braid. So there's more history, and as I said here, there's even older example of knotting. This is kind of story from Gilgamesh, I think, story or something like this. Anyway, the snake really, but it's very nicely knotted. And this is older. This is, as we see, 2600 BC, so almost 5,000 years ago. I think this is the oldest I could find clearly knot and on purpose knotted. Snake is on purpose knotted. Okay, here is this long description about the oldest knot used in science. So I moved long description, but let's see the picture. The picture is relatively modern from still Greek description, but it's from Byzantium, where this description of knotting by Sargeron knots stayed. This has again nice history. So this writing, ancient writing, survived, but no pictures. So in Renaissance, people were trying to recover this knot from description. I will maybe put description under the picture. This is, of course, translation of translation. And people were disputing this and etc., etc. This is the simplest of them. It's just keeping the bone, how to keep bone in position. But there were much more complicated description, and people till now dispute what really was the knotting. Probably this is not well discussed in research, not theory, but it could be. I will go further to history, and we'll see that now some mathematician, maybe even at Congress of Not Theory, were thinking, yes, this is about Leonardo and Dürer. So Leonardo da Vinci was, as known, very attracted by knots, and whenever he could, he put some knots, probably with some mystic value. So this is the knot of Leonardo, which is well known, with note Academy of Leonardo. And I think at least few, one of them was Harari, I think Ken Millett as well, were trying to see, first of all, what type of knot it is. Quickly they discovered there's a link. So what kind of linking here is? And it's very interesting. So anyway, I think it is Harari and Ken Millett. Okay, and Dürer was follower in this sense of Leonardo, and he was producing this fall knots or maybe links. One of them is identical with Leonardo da Vinci. Other are maybe his creation, or at least we don't know about Leonardo. But they are for sure at least 10 years after Leonardo, after Dürer visit to Italy. So maybe there was really direct influence. That is fascinating topic. Knots. Okay. Now we go to Euler. I mean, first is, of course, Leibniz, this idea of geometria situs, and then Euler. Here is this Polonika that really bridges of Königsberg were first formulated in Gdańsk. There was Gdańsk mathematician Kuhn, who came from Königsberg. So this time it is not mysterious why Euler chose Königsberg bridges, because Kuhn really, through his friend Echler, told Euler about bridges of Königsberg problem. And they had correspondence, but really it is more than correspondence. Here I wrote all history, but I will not read these 2 pages. There was war about succession in Poland, and Russia took Gdańsk, and they had to pay big reparations. So Gdańsk sent delegation to Petersburg to lower these reparations. And then this Echler, who was friend of Kuhn, was in delegation, and he met Euler, and he was attending his seminars, and most likely then he told Euler about Kuhn story about problems of bridges of Königsberg. So let me jump, because this is several pages. As I said, history of Poland here, bridges of Königsberg, and now most likely the first mathematician who mentioned knots in scientific way was Vandermonde in 1771. Let me show this Vandermonde knots or nets closer. There were better pictures in Vandermonde paper. But anyway, he's just mentioning, maybe this I will read because it's really the beginning of knot theory as mathematical science. And he wrote, whenever the twists and turns of a system of threads in space, one can always obtain an expression for the calculation of its dimensions. But this expression will be of little use in practice. The craftsmen who fashion a braid, a net, or some knots will be concerned not with question of measurement, but with those of position. What he sees there is the manner in which the threads are interlaced. So exactly Vandermonde understands what should be important in knot theory. In fact, he refers as well to Leibniz geometria situs, that exact positions are not important, but only relative. Okay, now very soon come Gauss. So Vandermonde was 1771 and young Gauss is 1794. So that in very early age, he was 17 years old, he was fascinated by knots. And in his notebook, he has collection of knots. I copied here one of them. In fact, you can say even frame knot. So this is one of the knots by Gauss. So again, almost to connect with Lou. So it was Sofia Lambropoulou who invited me to Göttingen and brought me to old library in Göttingen, when to my amazement, they let me to go through Gauss notebooks. I took a lot of notes. They did, in fact, pictures for me, which I unfortunately now lost. But this I copied, the 10th knot of Gauss. And Gauss has many more. We know Gauss. Oh, Gauss, yeah, this Gauss I wanted to show. So we know about Gauss code, etc. Gauss was trying to draw knots. In fact, the fact that he drew immersion, not knot, was initially first pictures are really knots, therefore, etc. Then he realized that for alternating knot, there's no need to draw actual knot. It is enough to say that it's over, under, over, under. So he was drawing without. But this mysterious braid was not published in collected works. Probably people who did collected works in 19th century didn't understand the importance of this picture. But Gauss put not only this picture, but description, analytical description on every level. At crossing, he put position. Then once I was trying to check what is his eye is mostly going down the page, but in one case, by mistake, is going up. But anyway, he knew that it is just one page without even date in one of his notebooks. But this is now published. But this was not published at all. Frame tangle from Gauss' notebook, and we can only speculate what Gauss had in mind. Clearly, he's bending some frame thing. But what is this? We don't know. Okay, so probably I should go quickly through history. Then Maxwell initially didn't know about Gauss' work, but he gave credit to Gauss for linking number. So in his book at Electricity and Magnetism, there's this nice picture, which we call now Whitehead link. It has one more crossing, but then it is more symmetric. And Maxwell is commenting that linking number is 0, even if it is obviously linked. These two components are linked, but has 0 linking number. Then there were other discoveries which we should mention. Kirchhoff for sure should be mentioned. And as I wrote here, you can say much more. especially about Tate work and a little, and recent work of Boulton, who finished classification of knots up to 19 crossings and is extending this 20 or 21 crossings, but is not yet checked. So if I remember well, Boulton found more or less 150 million knots of 19 crossings. So as I said, maybe enough of history, of old history. So now I'm going back to HOMFLYPT, but I will do it very quickly. I just wanted to mention, it will be later. So here is my long way to non-associative homology and finally Yang-Baxter homology. So of course, if I like to go all over this, then it would be 2 hours, but there are various names. People ask me to work, but I was doing something else. So then work with Paweł Traczyk. And then this entropic condition. So maybe I wrote much more, but now I will make it much bigger. Entropic will be in the center. Okay. So you see this relation. Entropic relation is AB star CD is equal AC star BD. The role of B and C is changed. This reason that some people, and I am now following this, are calling this entropic condition, inner twist. So how we discovered this? Namely, when you have two crossings and you try to simplify using, say, HOMFLY relation, then when you change the order, instead of you have one crossing, then another, then on this abstract magma operations, when star is really saying what happened at the crossing, we switch the order of B and C. So this is not that new, as I wrote here, but it has long history because it has some Polonica, because it was first described, let me do it smaller. It was first described by Burstein and Meyer, and I was very curious who they are, and happened that Burstein was Polish and Jewish, Polish, and he did Matura in Tarnopol, I believe, and he went to Austria, and then he was working with Meyer and working with Einstein. So very shortly, but interesting story. Einstein was trying to find positions for them because they didn't have. For Meyer, he did find position in Princeton. Einstein said that he will not go to Princeton unless Meyer can go with him, but Burstein was communist, and I think that it was Einstein who arranged position for Burstein in Soviet Union, in Minsk. So Burstein initially was very happy, but then as happened in Soviet Union in 1970s, he was accused of being spy and arrested and was not executed because he died at interrogation. This is all in footnote. Here are this Conway algebra. You see relation ABC, ACBD. With Paweł, we didn't know that it was already started. I wanted to go to footnote. Oh, there's no footnote. Oh, there's footnote. Anyway, I should not talk more about this. I rather concentrate on this entropic condition. So in more complicated polynomials, let's say cubic relation or any relation, still we can check, is it possible to have some magma or not magma really, NR relation, and what condition should satisfy this MR function like you see here, x to m to x, so that our result does not depend on calculation. And here I learned this very nice concept, but it can be summarized by this picture. So we have this NR relation, or maybe even different. One is NR than MR. When you change the order of calculation, then in one calculation you go along rows. So here row has n entries, so take this NR relation. And then after all NR relation, you take MR relation. But you can change order and do start from columns. And this is really factual generalization of this entropic condition. So in fact, I think Jonathan Smith and people in his school are calling this still entropic, but more general. Yeah. So now values things which I was doing, but I don't like to spend much of time. I should finish soon. So values conjecture with tree moves, this tree moves. I spent all my life on this. In fact, it was the same Braid conference when I learned from Murasugi about Nakanishi tree move conjecture, that every link can be reduced. Finally, with my student Mietek Domkowski, we proved that is not true, that there's 20 crossing count example. And recently we proved that is the smallest count example, 20 crossings. But anyway, I should not talk about this because there's still, I think, 30 pages. I will go to the end. Gdańsk, you see, was here. Homology theory, then will be this approach to Yang-Baxter homology. I will show just one picture showing that really definition is on the picture. Picture will come very soon. Not yet, but almost here. Similar picture. Similar picture. Maybe I lost picture. Maybe this picture, but I prefer this picture. So you see, we define homology. We define homology as is shown on the bottom of the page, as usual, as alternating sum of face maps. And there's left face map and right face map, as we learned from quantum homology. And this is just saying what happened. On every crossing, we use Yang-Baxter operator. And this visualization should give almost the proof that it is really homology theory. Of course, I will not say one can look at this picture all the time, but I should go to the end. So this is computation with students, which I was showing at the very beginning, Yang-Baxter equation giving HOMFLYPT polynomial, and this is conjecture 8.4 is what we solve. And we even computed H4. And there are other conjectures numerical obtained. Okay, I think values interesting thing. And finally, picture should be happy birthday, Lou. So this is from Not in Washington 36 in May of 2013. So here I was in better shape and plenty of students. Some of you will recognize many people. You see, we see here Saito, and we see here many, Samlo Monaco. Probably we can recognize almost everyone. I will not test my memory. Okay, happy birthday, Lou.
Thank you,
So,
Professor Przytycki. I should end the video now.
yeah, many questions, yeah.
Yes, one moment to close the video.